Nagalakshmi is an engineering professional and delights in working at the intersection of people, processes, and technology. She has expertise in delivery excellence and an avid technology enthusiast who has recently completed her master's in AI/machine learning. Nagalakshmi's workshop is entitled Time Series Data Imputation, Generative Adversarial Networks Approaches. In this workshop, you'll investigate recent deep learning methods using GAN for imputation, relationships among those methods, and also see comparisons with advantages and disadvantages of these methods. She will answer questions at the end, so please add them into the Q&A as we go, and she'll share any resources after her workshop. Please welcome Nagalakshmi.
Hello, everyone. So glad to be here. And let me just start sharing my screen. So let's get started and welcome all of you to this workshop that we have today. And today we'll be covering a topic on time series data imputation, the approaches through generative adversarial networks. So with this, we'll get started. So what I would be covering today is what is indicated in the agenda here. So we will have an introduction to time series and the imputation in time series. We'll also cover the basics of GAN, and we'll see how the GAN-based imputations are implemented for time series. And we'll go over one specific implementation of the algorithms for one of the publicly available datasets called VSAT. Without further ado, so let's get started on the time series data. Let's dive in. So time series data is something which is omnipresent in our lives. It's everywhere, starting from weather forecast or stock prices, sensors, monitoring systems in industrial automation environment. Now, what is time series data? Basically, time series data is any type of information presented as an ordered sequence. So now time series is the data, which is your observation of behavior that's collected at different points in time and organized chronologically. So what is the central attribute? Time is the central attribute that distinguishes this time series from other types of data. So having time as one of the main axes would be the main indicator that a given data set is time series. How can we identify such data? There are three main characteristics that will allow you to easily identify such data sets. Like data arrives in a time order, and as we just spoke, time is the primary axis. Newly collected data is recorded as a new entry. So it wouldn't be an overstatement to state this, right? That the recent technological development we are having is based on our ability to collect and organize data, which was previously unseen speed and efficiency. That has enabled us to have a lot of technological developments. Being able to utilize this gathered data and understand, analyze, this allows us to build better systems and improve the efficiency of all the processes and predict future events in real time. Now, as we know, data is rapidly becoming one of the most valuable commodities in today's business world. And the importance of time series data is increasing as well. Now, organizations across the globe face the need to implement more IT systems, sensors, tools, all of which are able to produce, collect, analyze, and probably even predict some of the things using time series data. That's why it's so important to understand what this data series is, how we're using it the right way, how can we allow the organization to improve and optimize virtually all the work processes. So going forward in terms of the domains, being that time series is so omnipresent, it's obviously having a lot of different applications across various industries. starting from industrial companies with the digitalization of manufacturing, production plants, and you have related industries. There's an increasing amount of time series data coming across, right? Like examples could include time series data includes pressure, level, temperature, pH, as part of the various industrial automation. Next, coming to financial industry. So absolutely, many of the financial and banking applications that we use store and analyze time series data for multiple purposes. It could be like security, it could be support, and probably improvement of services. And some of the main things that we already see is the stock market trading, right? Which uses algorithms based on real-time data to optimize performance. Coming to consumer electronics, modern day consumer electronics is an industry which is rapidly growing with the appetite for data, right? Mainly due to electronic devices and systems nowadays that are becoming more and more complex and easily accessible. Now we have smart home systems, which has access to multiple kinds of time series data, wherein you're trying to identify humans, adjust temperature, detect intruders, things like that. We also have autonomous vehicles and robotic devices of various kinds that also use time series data as an essential component that allows them to move in space and avoid collisions. Now, coming to healthcare, we all know time series data plays a vital role in healthcare as well. So, with COVID-19 was an illustration of this, right? So, there have been many healthcare related procedures that rely on time series data, like your heart rate monitoring, which is your ECG, brain monitoring through EEG. Now, coming to retail. So, time series data is collected in various forms, even in retail industry. Now, this allows these enterprises to monitor the supply and delivery chains, which was not having so much of an efficiency earlier. The data about moving of various goods enables retail enterprises to optimize stock and provide consumers with discounts and services like the same day delivery. And not to forget the Internet of Things with the advent of the recent technologies. So basically, what we're saying is time series data cuts across so many domains across. And the applications are numerous. So this is just a source from one of the National Institute of Standards and Technology. But this is just not limited by this. We have economic forecasting, sales forecasting, budgetary analysis that we do, stock market in the finance world, yield productions, process and quality control, inventory studies, workload projections, census, utility studies, so many applications. Now, what that we face as a challenge when we go to time series data? So there can be incorrect or missing data, causes a challenge when we're trying to analyze and do predictions of forecasting. Why is this data missing? It can be due to various reasons. It can range from values not being available, there can be a missing sequence, you could have an incomplete information entry, you could have some kind of an error in the data entry, there could be some sensor malfunction in some sensors, there could be some communication gaps, errors, there could also be lack of storage space, connectivity issues. The reasons are numerous. So what happens is all of these will lead to non-availability of data, which would be useful if it was present. Now, what are the approaches, given that some of the data pieces are missing in time series? Most machine learning approaches deal with this by either eliminating or deletion or replacing, which is the imputation. Now, deletion can be carried out either list-wise or pair-wise, wherein mainly the samples or the features that are removed, which are partially observed, right? So it has to be considered that these deletion leaves gaps in the data set and results in erroneous analysis or parameter estimations. By contrast, the second method, which is the imputation, substituting these missing values with estimated values. Now, there are advantages of imputation over deletion. First is power. Notably, you have partial missingness in a single variable can still be informative for an estimate. Therefore, we should have a thorough investigation to contain all the relevant data. And if you compare with the elimination or deletion, that procedure may add bias. And properly stated imputation estimates will help us to get it into an unbiased state. So as downstream data processing relies on complete data sets, it's preferred to replace the missing portion with reasonable values instead of eliminating them directly. So that's where the imputation comes into play for time series data. So let's go ahead and try to understand what are the techniques that are available for the imputation. So the existing approaches to impute missing values can be broadly classified into two. The first one is replacing this missing data derived from the available existing partial data. So we have a set of partial data available, and we replace the missing data using the available partial data, like something using a mathematical model, like mean, median, mode, matrix imputation, or maximum likelihood. The second method is to replace the missing data derived from the prediction of missing data with a generated plausible value. So that's the second method. So first is the derived data, which is what we're talking about here in this slide. So it could be mean, median, or mode. And based on this, it may lead to an inconsistent bias, a loss of precision, especially when data is not completely missing at random and hence not valid. Or we could be using matrix imputation method, or we could be having maximum likelihood. Maximum likelihood estimation is a method where you determine the values for the parameter of a model. So if you recall, all of us are aware of Gaussian distribution. We have two parameters there. We have the mean, which is the mu, and the standard deviation. And when we give different values for these parameters, it results in different kinds of distributions and different curves, right? And we want to know which curve was most likely responsible for creating the data points that we observe. So maximum likelihood estimation method that will find these values of your mean and your standard deviation that result in the curve that best fits the data that we have. But point to note here is these methods are not being developed for time series data and hence cannot consider characteristics like your temporal dependencies, time decay, and feature correlation. So this is one of the types of imputation. Next, coming to the next type, which is the prediction of the missing data using techniques like deep learning, right? So here we have discriminative method, which uses conditional distribution like decision trees or SVMs. For this, we require label data, wherein time series data labeling is mainly focused on classification tasks to classify a particular behavior. The second one is a generative method, which is as per a joint distribution. So there are some existing techniques here, which is already available, which is like multiple imputation with changed equation, which is called mice, or we can have Gaussian mixture models, and we also have denoising autoencoders. So these methods are available for various generative methods. Now, if we see discriminative and generative methods are having complementary properties. Now, combining these two is where gives us the strength through generative adaptive networks, or GAN, as we call it, right? So this is where GAN comes into picture. This is just a sample to indicate how mice has been implemented using a scikit-learn library using iterative imputer class. So the previous slide, what we spoke about, it is one of the generative methods of prediction of the missing data. So we could use this that actually implements the mice algorithm, which is the multiple imputation of chain equation. Okay. So coming to the topic of GAN, which is the Generative Adversarial Networks here, right? So these are algorithmic architectures. They use neural networks. They use two neural networks that are pitted against each other. And thus, we get the name called adversary, right? They generate new synthetic instances of data, and that can be passed as the real data. And that is what we use for imputation here. GANs are widely used in image generation, video generation, and recently the text generation that we're all aware of using the generative AI in the ChatGPT. GAN was introduced by Ian Goodfellow, and this framework has two parts. The first part is a generator. We call it as G sometimes, or generator, right? And a discriminator called D. Now, the generator is fed with, as an input, a random noise, which is based on Gaussian distribution. And the output of the generator is a synthesized data, which is created such that the generator has captured the distribution of the real data. Now, this completed vector data, whatever is generated by the generator, along with the real data, is fed into the discriminator. And the discriminator uses both of these data sets as input and learns to classify whether this input data comes from real distribution or if it is a synthetic data generated from a generator, and learns to distinguish this. Now, the objective of the generator is such that they need to minimize the difference between the completed vector data and the real sample. So it can be passed off as if it is real data. So the main objective is to minimize the difference between the completed vector data and the real samples as much as possible. And the ideal state is when the discriminator just cannot discriminate between whatever was the completed vector data set and the samples from the real distribution. So for training, the generator is fixed while the discriminator is trained, and vice versa as well. So this strategy of having the generator and discriminator, they play a min-max criteria, is provided in the next slide that we'll just talk about. So this is the one that is being predominantly being used and explored further for even time series data. But when GAN was designed, it was not designed for sequential data, and we cannot use this directly as is. And we need to explore to see what we can do. And there's been a lot of research that has been going on towards development of hybrid models that use GAN as an underlying global concept. So this is the mathematical model of GAN that we just spoke about, wherein we are having in this equation, we say G, which is the generator, and D is the discriminator. The input to the generator is random data, which is used as Z here, and discriminator also has an input coming in from real data, which is X. The distribution of the generator is represented by the PG, and distribution of real data is the PR, that's represented here. GZ is the generator network, and DX is the discriminator network. The expectation of the distribution of the real data and the expectation of the distribution of the generated data is provided. So what we do here is we train discriminator to maximize the probability of correctly predicting the data, and we train the generator to minimize the probability of discriminator predicting this data. We'll go through the details as we proceed. So how does GAN training happen? The training of discriminator happens on the real data first, and then the generator generates fake inputs through the generator, and we train the discriminator with this fake data. And then we train the generator with the output of the discriminator. So in GAN, for time series, there have been two existing models coming in around the time of 2018 or so. So BRITS is one of the models, which is called bidirectional recurrent imputation for time series. Bidirectional RNN. And we train two models in the forward and backward direction. And the next one, which is the NEOMI, which is non-auto-regressive multi-resolution sequence imputation. So these are the two key techniques that use GAN as the underlying core theme there. And both of them are the initial techniques that have been proposed. And in BRIDS, the authors, they propose, as I said, the bidirectional recurrent neural network, wherein they train two models in forward and backward direction, and losses in both the directions are taken into consideration. It also uses a temporal decay factor to deal with irregular samples. In the second model, the authors proposed a generative model that uses non-autoregressive. Non-autoregressive is what? The autoregressive is where the output of autoregressive model is dependent on the model output of the previous sample. But in non-autoregressive, you do not. So in the second set, which is NOVI, we use non-autoregressive multi-resolution method. It comprises two components. It has an encoder that maps the time series to incomplete data to a hidden representation. So they take the time series with incomplete data to a hidden representation and a decoder which considers these hidden representation into the imputed values. This method has a limitation because they're not aware of irregular time series because of using non-autoregressive. And due to the fact that gaps in time are not considered, the RNN model has time series also without timestamps. So there are disadvantages with the existing set that was already there. And there are also challenges when we use GANs for time series data, right? So one of the challenges is instability. A model that does not converge but continues to oscillate is one of the challenges that the models face. Or you could also have a diminishing or vanishing gradient. What happens here is when discriminator is very successful in being able to distinguish between real data and imputed data, it prevents the generator from learning and it just has a diminishing or vanishing gradient. The third challenge is a mode collapse, wherein the generator is collapsed by producing only uniform samples with less or no variety. Also, one of the challenges for time series data using GAN is the evaluation metrics. There's just been no agreement across the various studies of work of research. And many of the matrices are being used across, so easy comparison is not available. So if you see here, many of the works use mean absolute error, which is average of all the absolute errors we get. Or they may use RMSE, which is the root mean square error. Root mean square error, as we all know, is the standard deviation of the residuals. And they also sometimes use something called as fractional standard deviation, the ratio of the standard deviation and the mean of the distribution of the random variable. There's also a couple of studies which use generator score and a discriminator score, where generator score is the mean of probabilities corresponding to the discriminator output for the generated images, or discriminator score is a mean of probabilities of input images belonging to the correct class. Sometimes we also use special distance, it's a measure of similarity between the curves that takes into account the location and ordering of the points. So net, all of these, many of the methods that are used for time series data using GAN, the evaluation metrics is not standard. And the main thing is we need to ensure that there's stability between generator and discriminator. Because if discriminator is powerful, the generator will fail to train altogether and cannot push fake samples. And if discriminator is very lenient, anything from generator will make the network useless. So today, there are some of the GAN types that have come out beyond what we already had, which is like on the right side, you see gain. We'll go over that today, which uses a concept called hint matrix. And there's something which is on semi-supervised side, which is SSGAN. And on the right side, you see sting. We'll go over that as well today. It uses a dual generator and attention layer. There are a couple of GAN models that are developed, which are domain specific for wind power and other kind of data sets. They use bidirectional GRUI or recurrent neural network. We'll not cover those today, but I just wanted to indicate that these kind of developments are happening in the area, and we can just try to understand how GANs can be used for time series. With this, I'll go to one of the first models that had got a lot of prominence when it was started off as a research area in 2018, which is called GAIN, which is nothing but expands to Generative Adversarial Imputation Network. And we will also go over a code walkthrough of this today. So this setup, what we see on the left side, is very similar to a GAN. We see a generator, we see a discriminator. Now, if you see the generator, it has a data which is fed into it. It also has a random matrix, which is called as Z, which is very similar or analogous to the noise that we feed in the generative adversarial network. So along with that, we'll also see something called as mask matrix. We will go over that too. So if we see here for the generator, it is fed with data matrix, a random matrix, and a mask matrix. We should note that in this framework, the target distribution is essentially a 1 minus m distribution. So this mask matrix is representing the data which is missing from your original data set. So if you see all the missing data which is marked as the original data, which are marked as all marked as zeros in the mask matrix. So if we take 1 minus m of that and do a dot product of that with a random matrix, we will be able to have the random data fed in for those particular data sets, right? So this is mainly done so that the dimension matches to that of the target distribution. Now, if you see here, we have another green box here called hint generator. So this one is a hint mechanism, which is a random variable that is taking values that depend on the mask matrix. And this is given as a hint matrix as an input to discriminator along with the imputed matrix. So this one will help the discriminator to identify which one is generated data and which one is a real data. So as in the GAN framework that we originally saw, we have this discriminator. It will be used as an adversary to train the generator. However, unlike the standard GAN that we have, wherein the output of the generator is either completely real or completely fake, in this kind of a setting, for time series, the output is comprised of some components that are real and some components that are fake. So rather than identifying this entire vector as either real or fake, the discriminator attempts to distinguish which components are real, which components are fake or imputed, right? So this amounts to nothing but predicting the mask vector itself that we already had, right? So we see that the output of the discriminator is an estimated mask matrix and not a classification kind that we had of a single output, right? So this is the one that is going to be used in terms of a loss for cross entropy back to the generator. Right? So we should note that mask matrix on the top before the generator is predetermined by the data set, but the estimated mask matrix is what we're looking at to see how we can train this. So we train the discriminator to maximize the probability of correctly predicting the mask matrix, and we train the generator to minimize the probability of discriminator predicting the mask matrix. So this is the primary concept based on which many of the models in time series data using GAN are built upon. So this was one of the pioneers that came out by the authors in 2018. And it was considered state of the art, SOTA is state of the art. and it had performed consistently in multiple time series data from the UCI datasets. Now, going to another model, which is semi-supervised GAN, right? So here, this is very similar to the previous models we had in Naomi on BRIDS. It adopts the bidirectional structure to capture the temporal information. So if you see here, we have a generator, we have a discriminator, but we have an additional component here called as a classifier. All of these are made out of bidirectional RNN cells. So now SSGAN takes 4 inputs. If you see here, it takes the incomplete time series data, which is what we want to look at for imputation. It contains a data label matrix to identify which are the missing pieces of data. It has a mask matrix and a time lag matrix as well. So the classifier takes all of these inputs. They're trained with this labeled time series data to predict the labels for the unlabeled samples. So if you see, there are missing labels for X3 and X4. So the classifier is trained to predict the labels for this unlabeled sample, and it sends the feedback in the form of cross entropy to the generator. Now the generator predicts the missing components of the given data based on the observable components that we got. So we have X1, X2, Y1, Y2, X3, X4, which are the inputs, and Y3, Y4 are the labels for them, right? Which was generated by the classifier. So it uses that, and what it also does additionally is it enables to focus on samples with the same label while imputing an incomplete time series. So the imputed matrix that is generated is given as an input to a discriminator. The discriminator works the same way that we just spoke about even in the previous time. Right? It has a mask matrix, a temporal reminder matrix, uses the imputed matrix to find out what is a discriminator matrix, which will be fed back to the generator. So the difference here is the use of classifier and the generator using the predicted labels to generate the output. So SSGAN outperforms the others and deep learning imputation like BRIDS and U. However, there's been no study that has been done to compare the performance of this with GAN, and there are no reported limitations of this approach. And this is another model called STING. STING is expanding to self-attention based time series imputation network using GAN. It's a lot of words, so we'll deep dive each one of them. So this is an improvement on GAN that we just spoke about, and we'll try to see how and why, right? So here they have two generators, one in the forward direction and one in the backward direction. And we have in here, the STING takes 4 input matrices, similar to what we had spoken before, right? So it uses the data matrix, the random matrix, the mask matrix, and the time gap matrix, right? So all of these are used and used for both the forward and the backward directions. And both directions complement the lack of information problem that used to come when they were using a unidirectional structure. So mask matrix, as we know, it serves to inform the generator of which elements of the input X are observed and which are missing. And now time gap matrix is nothing but a temporal information which says to the generator how much you should go back in the previous hidden state in case there are missing values arbitrarily. So now if we go inside the generator, there are two types of attention layers here. So there's a self-attention module. It produces something called as context vectors out of the input sequences. So what this does is it calculates the attention scores at different positions and captures this correlation within the sequence. So if you just think of it, it just gives you a context vector. It has the correlations within the whole sequence, and that's what it gives out. Now it is fed into a temporal attention module, which represents this correlation between context vectors and the hidden states of the network. So it does a correlation of that, and also has a temporal decay layer into the generator. So all of these are provided as a working mechanism within a generator. Now, at the end of the generator, we get an imputed matrix, right? We also have a hint matrix similar to what we saw in GAN through a hint generator. So both the imputed matrix and the hint matrix are fed into the discriminator, and the GRU discriminator has a simple design as compared to what we saw in the generator. The generator has so many things going on here, and it outputs a probability of being original or reconstructed for all components of matrices like SSGAN. So as per the experiments that have been conducted as part of this study, it is reported to be the best in class as even compared to GAN that we just spoke about and other deep imputation methods. However, it has been tested with 3 UCI time series datasets, but any further study that can include more data domains will ensure that or give us contrasting information if this really is the SOTA. And there are no known or reported limitations of this approach. So just to give a summary, in terms of the methods, the year, and what method they use and what data sets they have used. All the methods we spoke about, we didn't cover solar and the wind power. They are very domain specific. But yeah, they use a similar concept of GAN. That's how they developed as well. So GAN started all of this in 2018 with the GAN method and has used 5 different data sets. Solar GAN and wind power came subsequently in terms of domain specific. They use specific solar data and wind power data. And SSGAN came out subsequently in 2021 with GAN as a classifier, and it was verified with the UCI time series datasets. And STING, which we just spoke about, came towards the end of 2021, where GAN with 2 generators, attention layers, temporal decay, all of those were used. It was being verified with 3 datasets as well. Now, if we see in terms of advantages and disadvantages, we see that GAN was previously the state of the art, very generic algorithm where people are utilizing it for very domain specific, variants, and no disadvantages. But I think there are algorithms, as we see, like Sting, which are improving the performances based on what GAN have. The code is publicly available through the paper that has been published. Solar GAN and wind power GAN, they are better than GAN in those specific use cases itself, and they're not very generic. So we have the code link available for Solar GAN for people who have tried it. In terms of SSGAN, we spoke, it is better than BRIT and NUMI, and it is mainly for label data sets, and there's no comparison that's available with GAN. And Sting is currently the state of the art and is a generic algorithm, and there are no disadvantages currently known or documented, and code link is currently available. So with this, I would want to spend some time as part of the workshop to go over to see how GAN has been implemented. And I took in a data set from the public data set from the UCI for the variable stress and effect detection called VESAD. So it's a multimodal data set which features the physiological motion data. They recorded from the wrist and the chest wall device for 15 subjects during a lab study. It has the sensor modalities like blood volume pulse, electrocardiogram, electrodermal activity, respiration, body temperature, things like that, right? And moreover, the data set bridges the gap between previous lab studies on stress and emotion. And it has 3 different affective states called neutral, stress, amusement, things like that. And this data set does not have any missing values. So we will have to generate or simulate the missing values and then check it out. So that's where we are on that. And based on this, I would want to just switch and share the code so that we can go over that. So let me just pause, stop the share, and share the code that I have that we can go over. Okay. So this is the code that uses the VESA dataset for the GAIN algorithm that was provided by the authors and also been available from the original implementation using TensorFlow. So if we just follow through, I'll also run the code as we progress through so that we can, and I'll also have the code shared across as well. So we start off with importing all the packages that we require here. And they are the general packages that we have, which is the NumPy, the TQDM, Pandas, Matplotlib, CSV, and the splitting of the test and train. And yeah, I'll just ensure that we use the GPU, and I'll need to mount my drive. I'm running this on Google Colab. And to get the VESA dataset, it's available in the UCI website. I've given the link in the notebook as well. So I have downloaded that onto my drive and I'm loading the same here. So if you see here, it has a lot of signals and data in terms of chest or wrist and what kind of signals is it, ECG, EMG, and data sets like that. I load that onto a data frame. And if you see, there are about 9 of these data and a lot of information that has come for this. The amount of instances are huge. So this is how the data looks like. And there are some outliers which I just would want to extract it out in order to just and also do some normalization before I take it forward there. So this is just ensuring on some of the basic information that we see here. And we start with the system parameter setting here. So I take a mini batch size of 2048, which I've just hard coded here. And since I need to simulate the missing data, I take the missing rate as 20% here because this data does not have anything missing. I need to simulate it. And as you recall, in GAIN, we had a hint matrix. So we need to generate the hint matrix. The rate I have just chosen 0.7. And some of the hyperparameters like alpha and training rate are also given here. So we also go about starting introducing the missing here by taking the missing rate and generating the missing matrix here. Yeah. So the missing matrix is multiplied by a minus 100 based on the randomness that we have generated. And we use that as part of the input that we have for the game. So we also distribute the test and train, the test features and train features for the normalized data set that we have is also given, and the missing is also divided across train and test. So necessary functions are set up, and we also have a hint vector generation that is there to generate the hint. Now, as we know, GAIN contains 3 components, which is the generator, discriminator, and the hint mechanism. So if we just go to the generator, it requires the data. It also requires the mask. So that is what we are generating here by having the tensors being set up. And we will go through the generator and discriminator here. So generator uses a mask M and the data that we have, which I'm just passing it to the generator. And I will just take this output and I'll use that. Similarly, discriminator will also be using, along with the data, it will be using the hint matrix. That's what I'm using here. And I'll take the matrix here and multiply it and consider the same. We need to also have a random sample generator for Z that we just spoke about, which is an input for the generator. So we just take some random samples from a uniform distribution. And we also have a mini batch generation function that is available. So now what we do is, as part of the entire algorithm, we need to call the generator. We do as part of the discriminator loss. We call the generator, we take the input and the mask matrix. And as you recall, we told that to match the output size, it has to be 1 minus the mask of the sample that we have taken and add it along with the data that we already have, and pass it along to the discriminator with the hint matrix and try to find out what is the loss. So similarly, we find it for, I think I just brought up, for the generator loss as well. We take generator, which has the input X and the mask matrix, and we combine it with the original data, which is your X, which is, we call it as new X here, into the mask, and 1 minus of that with your sample that you just got. So once you combine it with the original data, send it to the discriminator along with the hint matrix, find out the loss and feed it back in. And that's what we're going to be doing now. Let me just run this. Yeah, and we'll also compute the performance metric in terms of the equations that were given there, which is 1 minus the mask into your input, and we'll take the 1 minus mask of the sample that we had, square it out, and take the mean of that. MSE test loss is what we'll consider. In terms of optimizers, we'll use the Adam optimizer for the generator and the discriminator and start the training. So here I am considering, in the interest of time, about 1,000 epochs, but we can ramp it up as we require, and we will try to see how it goes. While this runs, I'll just walk through this. So here we take the sample, the training, and the training X that we had in terms of what we had from what we split between training and test. And we take the sample of Z, which is the random generation for the input for the generator. And we also consider the training of M, which is the mask, right? And we combine all of these into hint matrix, which is M into H of MMB. And yeah, this is the one, right? So the mask into the input plus 1 minus M of that into the random generated input. And that is what we'll be using here. And we will directly call the discriminator loss. As we saw, discriminator loss first calls the generator, and it subsequently calls the discriminator and feeds the input or the loss back into the generator. And that's how we will be computing. So if you see here, we will be seeing we're considering only the intermediate losses. I am currently running about 300 odd epoch out of 1,000, but we can ramp up the epochs as well as we see. So if we see here, the test loss is reducing, and we'll see where it stands when it completes. So this will take a little while, maybe a minute or so. Yeah, we're almost halfway through. And we'll also try to draw a graph in terms of how the loss function for generator and discriminator works when we are looking at this time series data as well subsequently. So we're almost there. It's about 80% done. Yeah, we're almost there. And then we can test it with the test data that samples that we had taken. And similar thing, we introduce the missing data using the mask metrics and the random sample that we generated, and use the test data that we had. Yeah, this is done. Then we just tested the test set that we had, and we get the final RMSE output, and we can also see the imputed data. Even though we synthesized it, but yeah, it just shows what is the imputed data that we had, that we got after this example. So yeah, these are some samples that are generated. And we can also see the graph of the generator loss as we see over the epochs, right? So this is 200 and this is about 1000. So the generator loss is reducing by about 200 epochs, and then by about 400 epochs, it's completely reduced drastically, and then it settles by around 800 epochs. But yeah, we can continue the training for more epochs and see how well we can train this further. But in the interest of time, I've just done it. And similarly, we can see the discriminator loss too. Yeah, so this just drastically reduces and settles by around 700 or so. Yeah, then we can, again, as I said, we can just continue to see how it performs going forward. So this this is the walkthrough of the code of GAN that we had, and I have tested this with multiple inputs from the UCA dataset, apart from what GAN had already done in terms of the 5 datasets. So this was one of the datasets that was also available. But yeah, we can try it out with a lot of other datasets as well, and see how it performs and do a comparative study. So this completes the topic that I had, and I'll just share my LinkedIn also, and we can see if we have some amount of time for any question and answers.
Well, I want to be the first to say thank you, Nagalakshmi, to us because this was a lot of great information. I remember running GANs and I typically use an external GPU. So just seeing that with Google Colab and seeing it run online was great to see. And in terms of questions, quite a few of the participants do have questions that are in the Q&A panel. And one of the items is we're also trying to see about time. So it looks like for the Q&A panel, we do have time for at least one question. And if you could stay online, Nagalakshmi, and maybe answer the other questions offline, that would be helpful. We can also collect the questions too and send them to you. So we can do that. But let's see about possibly answering one of the questions before our next presenters join us. So I'm actually going to not go in order. I see one question that I think may resonate with a lot of the audience members. So here's this one question. For a person who doesn't know about GAN, where can we learn about it?
Yeah, I think, yeah, there's a lot of material, I would think, but yeah, I'll have to curate and share it to Mithali. I see that Mithali has asked this question.
Yes.
But yeah, there's a lot of material on GAN. I think we just get lost. Ian Goodfellow is the one who introduced it. We can just share. Okay.
Absolutely. And then in addition to that one person, I think a lot of the audience members, because they may be at different stages learning about GAN, can definitely benefit from the resources that you're going to share with us. So that's great. And there are a lot of resources. So we'll see that information. And right now we're about a few seconds before the next presenters. So with that, Matt, I want to say thank you once again to Nagalakshmi for sharing her expertise with us. She will be sharing resources after this presentation. And keep in mind, the presentation was recorded. So this recording will be uploaded with Nagalakshmi's presentation. Thank you once again, Nagalakshmi, for sharing your expertise with the WIDS community today.